So good morning everybody, myself Acharya Vishwendra. This is NCRT line to line discussion and let's start with question number 247. So it says that when V is equals to breakdown voltage, the diode reverse current, so it increases sharply due to breaking of the bonding electrodes. So second will be correct over here. Next is when V is equal to VBR, slight increase in bias voltage leads to obviously large change in current. So first is correct over here. Next is in reverse biasing. If reverse current is not limited by an external circuit below the rated value, the PN junction, obviously it will be destroyed due to large amount of heat produced. Next is in the above question, if the external voltage exceeds the rated voltage, the diode will get destroyed due to overheating. So first will be correct over here. Next is a PN junction. A PN junction diode can get overheated only during. So it is very possible in both the biasing. So third one will be correct over here. Next is we are being shown some biased just the barrier voltage, and three different cases are given. It's for an unbiased PN junction under forward and reverse bias. So here the without biasing the barrier voltage is A. So under forward bias we know that it decreases, so it will correspond to C, and under reverse bias it increases. So first will be correct over here. Next is for studying IV characteristics of a junction diode, we use a potentiometer so that applied voltage obviously it can be a variable. Next is for current measurement we use both milliammeter as well as microammeter. Milliammeter for measuring forward current and microammeter for measuring the reverse current. Next is in the above question, during forward biasing obviously we use milliammeter as current is more, and during reverse biasing we use micrometer. Now is to study IV characteristic, emitter used in A and B. So here in A you can see that this is P side and this is N side. So P is connected to positive side, so this is forward biased, and here it is reverse biased. So in A we will use milliammeter and B micrometer, so second will be correct over here. Next is IV characteristic of a PN junction is, so this is obviously shown by first, as forward current is in milliampere and reverse current in microampere. Next is in the above question, during forward biasing, current first increases very slowly, then exponentially. So it is given by the first. Next is voltage after which current increases exponentially in a PN junction is called, so this is called the threshold or the cutoff voltage, the cut-in voltage, sorry. So third will be correct. Next is threshold voltage for silicon and germanium R. So it is given by the first option. Next is in reverse biasing of a PN junction, the current is called obviously reverse saturation current. Next, under very high reverse bias, so obviously it will break down, so current suddenly increases, first is correct. Next is general purpose PN junction is used, obviously it's before the reverse saturation current. Next, PN junction diode primarily allows obviously flow of current in one direction, first will be the correct option. Next is For rectification of AC voltage, the used property of junction diode is that obviously forward resistance is low as compared to reverse bias. First is used. Next is dynamic resistance, so this is delta V by delta I. Dynamic resistance means that V and I both are changing abruptly and non-linearly. So we replace V by delta V and I by delta I. So dimensionally it will be equal. Next is IV characteristic is shown in the figure. Diode resistance at 30 milliampere. So this is the dynamic resistance. So for dynamic resistance we will use delta, the concept of delta ID. So here current is 20, here it is 40, so 30 will lie somewhere in the middle range. So we take reference as this. So dynamic resistance will be delta V by delta I. So as you can see, the voltage is 0.8 over here and 0.7 over here. So difference will be 0.1 divided by delta I will be 40 minus 20, which is by 20. And since this is in milliampere, so we have 10 is to power minus 3 over here. So it will be equal to 10 is to 100 by 20, and which is equal to the 5 ohm. So first will be correct. Next is diode resistance at VD is equal to minus 20 volt. So here we can use directly the property that R is equal to V upon I. So V is 20 here and I is 4 microampere. So that will be 10 is to power 6. So if you solve it, it is 5 into 10 is to power 6 ohm, which is given by the first thing. Next is the circuit used to rectify AC voltage. It's also called as the rectifier circuit. So second will be correct over here. Next is if an AC signal is applied across a PN junction diode in series with a load, then a pulsating voltage will appear across load when diode is, obviously it will conduct when it is forward biased. Next is the above circuit is called, it's called the half wave rectifier. Next is the ratio frequency of output and input in the above circuit is, so it is 1:1. Next is the reverse saturation current of a PN junction diode is, it is quite negligible. So first is correct. Next is for using PN junction diode as a rectifier, the reverse breakdown voltage must be sufficiently higher than P. Obviously first is correct. Next is the figure shows a half wave rectifier circuit. Here one represents, obviously it represents the primary coil. Next is 2 represents, so it represents secondary coil, second is correct. Next is 3, so 3 is basically the transformer. Next is 4 represents, 4 is the load resistance, so 4 is correct. Next is we are being given voltage at A is given, output voltage, so this will be half rectifier, so given by second. Next is rectified means, so it's mean restricted in one direction. Next is if 2 diodes are used, then we have a full wave rectifier. Next is center type transformer, obviously it is used in full wave rectifier. So second is correct over here. Next is the above, here 1 represents, so 1 is the center tap. So here 1 is the center tap, 2 represents center tap transformer. It used by using